Ça va? Pas de problème? Well, good morning, everybody. I welcome you at this talent course, second talent course at Ganil. I'm very glad that you find your way to this room. I hope you have taken the breakfast in the restaurant, that you did not miss the restaurant as well. And probably you did not sleep under the bridge, so you were sleeping in your dormitory. So I'm very glad that I counted. You are 31 person as it should be, so I'm really very happy that everybody arrived. We do not know each other yet, but we will ask to introduce ourselves later. I'm Marek Płoszajczak, I'm one of the organizers, and I also welcome you in the name of the Talent Steering Committee, which is proposing this type of courses in different places in the Northern America and Europe. The TALENT is an acronym for the Training in Advanced Low Energy Nuclear Physics, and that is what you want to really get this training on methods on nuclear theory which are necessary to understand experiment in this course. Well, the TALENT initiative came from the observation that the systematic courses in nuclear theory, broad one, are getting less and less frequently at different universities where you take education, and then you go and start your PhD studies with relatively limited knowledge. So the idea of trainings of talent type is to provide this very broad curriculum which will take you also outside of your particular interest in when you prepared your PhD thesis, and give you the broader knowledge of different methods and theory that are important to understand the nuclear structure and nuclear reactions. There is a broad spectrum of subjects that are being covered, and they are also having the interdisciplinary aspects in them. Which means that just the methods, the theory methods and techniques that you are learning at this and other courses, talent courses, can be used also to understand other many-body systems and get an insight into complicated quantum physics problems. The whole curriculum, the whole system of talent courses has been divided in 9 programs, 9 courses. The first one started in 2012 at ECT STAR, which is an acronym for European Center for Theoretical Studies in Nuclear Physics and Related Areas in Trento. So the course number 1 is on nuclear forces and their impact in nuclear structure. The first course of this kind was organized last year in the Institute of Nuclear Theory in Seattle. Course number 2 is the many-body methods for nuclear physics. This course will be organized at Ganil next year. Course number 3 is on few-body methods and nuclear reactions. This course will be organized next year at ECT STAR in Trento. Course number 4 on density functional theory and self-consistent methods has been organized this year at ECT STAR. Course number 5, Theory for Exploring Nuclear Structure Experiments, is the present course. Course number 6, Theory for Exploring Nuclear Reaction Experiments, has been organized last year at Ganil. Course number 7 on Nuclear Theory for Astrophysics has been split in two parts. First one was organized this year at Michigan State University, and the next one, the second part, will be organized at Institute for Nuclear Theory in Seattle next year. Course number 8, Theoretical Approaches to Describe Exotic Nuclei. This will be probably in 2016. And course number 9, High Performance Computing and Computational Tools for Nuclear Physics. This this course was organized in 2012 at ECT STAR in Trento. So you see, this is the whole spectrum of subjects. Each of them correspond to 3-week extensive and a very intensive courses that you also are going to have this time. Now, concerning the present course, first of all, I would like to congratulate that you are here with us, because there were many applications, and we had a lot of trouble to select the person for this course. We are very happy that you are with us. And this is, of course, a privilege, and with all privileges there are related duties, and the duties that are, it corresponds to make all efforts in order to profit from these courses as much as possible. And to profit from the courses, you should not be shy. There are the best teachers in the world in this subject, and there will be exercises and lectures. You should really come and you should ask them. I have been asked by Professor Rick Kasten, that you should also stop him when during the lecture, ask the questions eventually. So, I mean, you should use your time, these 3 weeks, in the best way possible, in order to learn as much as possible to understand best the nature of these complex nuclear systems and their manifestation in the form of spectra, transition probabilities, and collective variables. More details about this, the course, probably the courses and the projects you will get in the next presentations of the teachers, of Rick Kasten and Piet van Isaker here present. What I would just only like to say is that if you want to obtain the credit for this course, you have to submit a project that has to be accepted by teachers, and on the basis of this project that will get some note also. That means it will be evaluated by all teachers. You will get a certificate which allows you to ask for the credits at your university. You get official letter from the University of Caen, which helps you in this aspect. Now, a few practical issues. Caen is a medieval, very old city. It was very heavily destroyed, but still the main, during the Second World War, but still the main architectural monuments, like the castle of the William the Conqueror, the two famous abbeys for men and for women, they are still there, a really fantastic architectural monument from 11th century on, and I think you should also enjoy to be in the city and to learn it. I mean, this is not for us as organizers. It's not our problem. What are you doing in the evening after courses, after having all the load of information? As you know from the information we have sent before, during the week, that means during the days of the courses, all meals you take here in the restaurant of Ganil, breakfast, lunch, and the dinner after the courses, which will be, I think, from 6:30 or 7 o'clock. You have to leave Ganil at 8:30 in the evening. This is some kind of external constraint. But anyway, I don't think you want to sit down until 8:30 and over your exercises they are not finished and so on. You may have some practical problems or questions. You can get help from the secretaries. Today you have maybe met Sophie Montalon, but later on, next week, she will come. You will get the answer you will get also help from other secretaries. This week is a shorter week because Friday, 15th of August, is a national holiday. It's an excellent occasion either to sleep over your jet lag or to visit Caen or Bayeux, which is just only 20 kilometers away from here with the fantastic tapestry. So this is on 15th of August. You cannot enter here. You'll get your meals in the dormitory, as it was also describing information you've received. And you cannot enter Ganil. On Saturday, 16th of August, we'll have a small one-day excursion into Normandy. We will see Saint-Malo, we will see Mont-Saint-Michel, and we leave early in the morning. Early in the morning means 9 o'clock, and we come around 7, 8 o'clock in the evening back. Finally, there is a web page which will be dynamically evolving. There will be very serious things there, like lectures, registered lectures. These registered lectures actually are part of the material that is being collected from each course of the talent, and will help also future professors, teachers that want to make similar courses at their local universities to prepare the courses. So there are the serious things and like material, but there is also a more kind of something that will manifest our life during these 3 weeks together. And so, for example, if some of you is making pictures of your colleagues, you can make also the picture during during the lectures or exercises. The selected number of them can be put on the web page as a kind of a element to keep our memory. Just before I finish, I want to say you that this 3 weeks together with all your colleagues and also professors it could be a marvelous occasion to have some memories for the life. You know, you do not only learn, of course, that's a fantastic thing to learn, and it's for why we are here. But you also you'll have colleagues, you will have friends that hopefully you can meet afterwards for 30 or 40 years. In your career, hopefully successful career as a scientist or researcher, and I don't know. But anyway, these early contacts, these early friendships are usually, they stay for life. So I just wish you that you have and the largest number of good friends, colleagues with whom you are working hard for 3 weeks, and with whom you will keep contact afterwards. That's probably all what I wanted to say. Maybe now Piet van Niezacker would like to take over.
I think I need this thing because we are really tape.
Yes.
Okay, good morning. So, like Marek, I also would like to extend my welcome to all of you. So I think we are complete actually. I mean, there is a maximum of people we can have at the computers. So for the exercises, there is a maximum of 30. So we had a very tough job of selecting from all the applications you guys. And so we are happy that all of you could come here. So this is very good. Now, so Marek gave an introduction to the overall program of talent. What I would like to do, and Rick also, he will complement me, is to give you a few practical things, how we will organize ourselves. And I think the first thing I should do is to remind you of the schedule, because maybe this wasn't clear on the web page. So the schedule we will try to follow every day is to start at 9 o'clock in the morning, right? And we go on until 10:30, and then there will be a coffee break. And so in the morning we will always have, let me call this lectures. So we will have a coffee break, and then there will be a second lecture from 11 to 12:30. Okay, so we have 2 lectures of 1 hour and a half each morning. And then in the afternoon we have exercise sessions. So we will try to keep this in, especially the beginning of the the first and the second, the beginning times should be because of some technical constraints we have. So this we should try to adhere to this schedule. And the exercises, they will start at 14, so we have lunch, 1 hour and a half for lunch, and the lunch is here a little bit further in the canteen where you had your breakfast, so that's not too. And then it's sort of, I don't know, we will see what will happen, but we will sort of end by 5, 6 o'clock, depending on how well you can do, on how fast you can do the exercises. And Vic will make some comments on what we expect you to do during the exercise sessions. So this is the schedule we will try to follow. All the lecturers will try to follow this schedule. So one thing which is important, there is a web page. So here is the name, and so on this web page we will put all material concerning the lecture. So this will be the slides, the exercises, any documentation. For instance, sometimes you will need some nuclear data. This will be put all on there. And there will be also, as Marek mentioned, exchanges about the social events. So all the information on the social events. And then if you want to put on pictures and things like that, that will be possible. So that's okay. So that's important for the organization, right? Because the information will flow through the web page. The last thing I want to mention, and this was also already said about, was already mentioned by Marek, is about the projects. So we encourage everybody to think about the project, right? And this probably related to their PhD project, or to their PhD topic, or something that is of their interest, okay? And if you want to get credits for this course, then the completion of such a project is a must, okay? So you have to do, in order to get the credits, you have to do, because this is the agreement with the university, so that's necessary. And so the way it will go is this week, the first week, you will have to think about a possible project that you would like to do, which is connected with the topics of the course, okay? And it's not only with Rick and myself who will lecture during the first week, but look at the syllabus of the total 3 weeks. See, okay, this lecture, I don't know, Marc Caprio or Jan Joly, this is sort of closest to my interest, so let me propose a project with, under the supervision of Marc or Jan. So you have to look at the whole 3 weeks and select something that is of most interest to you, okay? So that's, please think about this week. You have a long weekend to think about it. So, and then on Monday, next week, we will be more specific, and then we will talk with everybody, or the lecturers that you selected to work with, they will talk and sort of try to develop, I mean, from your idea, a project from that. Okay, and then the idea is to define the project during these 3 weeks. Okay, and then to finalize it within 4 weeks after the course. So you should submit something by the 1st of October. Okay, so during the week of September, the month of September, you work on this project and you should finalize it in the form of, let's say, like, think of it like a paper, right? A small paper that you submit to a journal, and so you write in the same way you write about your project, okay? And then it will be evaluated by all the lecturers or the lecturers that are in charge, and this will be necessary to obtain your credits. Is that clear to everybody? Because this is some important aspect for those who want the credits. But even those who don't need the credits, we encourage people to do this exercise. This is an sort of an interesting, sort of extended exercise, and it gives you some experience in trying to write a paper, to work on a specific project, etc. Okay, I think, yes, as possible, we had some suggestions of possible projects, right? But this, for instance, one thing is many of you are experimental people, so you try to work on a specific nucleus, right? And then you might say, well, what I will have to do in my thesis is then to make an interpretation of my data, right? Of what did I measure, okay? And so I will have to go to a search of possible models I can use to study such a nucleus. So you might have a project like that where you take not necessarily the nucleus that you will study in your thesis, but any nucleus you can consider and say, well, now I want to interpret this nucleus with the various models that I've learned about during this course. This would be a possible project. Another project would be study a chain of isotopes and look at the structural evolution of those isotopes as a function of nuclear number, right? And try to interpret the structural evolution in terms of some model, the shell model, or the interacting boson model. So that would be another possible topic. There are also theoretical topics, like, for instance, the tin isotopes. You can study these are isotopes where you have active neutrons in a major shell. These can be studied with an approach, a pairing type approach, and so you can, as I will explain in my lectures, you can study them using Richardson equation. And so then the topic would be the numerical solution of the Richardson equation in order to elucidate the structure of the tin isotopes. So things like that, right? But it's really something you should come up with ideas that are relevant to you. Okay, that is what we ask from you during the first week, to think about that. Okay, I think I'm finished. Rick will say a few words about other things, exercises, and then we will go and try to present ourselves, because we want to know who you are. Yes. Yes, this is to tape.
We're being taped by the NSA.
Possibly.
Okay. I want to be the third person to welcome all of you. We're really excited that all of you came, and we hope we have a good course. I want to talk a little about the exercises, but first I want to emphasize that, at least for me, but I expect for all the lecturers, we encourage questions. I have an acronym I always put up on the board, which is TINS task, which a couple of you know what it means. Riley, do you want to tell them what it means? Everybody hear that? There is no such thing as a stupid question. Many times students, young people in the field feel a little nervous about asking a question. But if you don't understand something, there's a good chance the person next to you doesn't, and you're both afraid to ask. So don't be afraid. Please ask questions. Okay, I want to talk a little about the exercises. The exercises in the afternoon will be at those tables, and there are 6 tables. 5 tables, that is. I was close. You should learn about experimental errors. And each one holds 6 people. We have roughly an equal mixture of experimentalists and theorists in the course. And since this course will focus a little more on data than perhaps some of the others did, I don't know, I wasn't at them. But obviously it's a course on nuclear theory, but nuclear theory looking at real data. So there will be theoretical aspects of the exercises and experimental aspects. And so we recommend a little more than recommend. May not be possible exactly because it's not exactly 50-50, that you will work in teams of 2, or you'll work, the tables are organized with 6 people, 2 on a side. We recommend that each pair of 2 have 1 theorist and 1 experimentalist. So that you can help each other with the areas that you're more familiar with. I think it'll go more smoothly. And as Marek said, you guys will be colleagues together for the next 30 or 40 years, and getting contact between experimentalists and theorists is a very good thing, and so that'll enhance that as well. Okay, that's all I want to say. Oh, no, one other point. Today, when we start the exercises, I will start with a few slides about how to get access to some nuclear data. Okay? Now, some of you will know that already. It's the NNDC, but I want to make sure everybody's on the same page with that. So we'll start here with 6 or 7 slides, and then we'll go over to the tables. I don't think they can see them too well from back there, so is that okay, Marek? Okay.
Oh, the slides will be on those screens.
Oh, well, okay, then if that works fine too then. Okay, now I want everyone to introduce themselves. I'll start off by introducing myself. I get the advantage of doing it with a photo, just a random photo. Very nice. Okay, well, it's a little... This is, yeah. I don't know if you can see that. Anyway, that's me in Antarctica last December. Okay. Can we have the lights back on now? Can you turn them up so people can see each other when they introduce? And then we'll turn them down. So that's me. I'm a professor at Yale. I'm a nuclear structure experimentalist. What I'd like all of you to do is give your name clearly and slowly, because probably for many of you, most of the people in the room will think you have an accent and therefore may not get the name very clearly, so say it clearly. And your affiliation, what institution you're at, what your level is, whether you're a master's student, a PhD student, a postdoc. I'm none of those. What your scientific interests are, and whether you're an experimentalist or a theorist, and anything about your personal interests that you think might be interesting to the others in the group. Okay, we'll start that in a second. I just want to point out these. This is my email address, richard.caston@yale.edu. This is Pete's, isacker@ganil.fr. This is the web page, which is already pointed out. Okay, so let's just go around the room. Might as well start here. Turn around so people can hear you. So just for, yeah. No, say who you are and, so, what your name is, your affiliation, your level, your scientific interests, and personal interests. Yeah,
I'm Yoshihiko.
turn around so they can see.
Hello. I'm Yoshihiko Kobayashi. This list this list is long. Correct is
okay.
Yeah. But we have to do this a little briefly.
yes.
Okay.
correct.
Okay.
My name is Yoshihiko Kobayashi from Japan. My university is Niigata University. I'm a theorist. And I'm interested in pairing correlation, especially.
Okay, thank
Very
you.
much.
I'm Guillaume Scans.
Say that again?
Guillaume Scans from Gamil. And I'm third year of PhD and I'm working on also pairing, but for dynamical.
Could everybody hear that? Okay, speak a little louder from now on.
I'm Kazuyuki Sekizawa from University of Tsukuba in Japan. And I'm a PhD student and theorist. And I'm interested in low energy heavy ion polymers such as multi-nucleon transfer reaction and quasi fission reaction and so on. Nice to meet you.
I would like to add that Kazuyuki was last year at this course and he presented the best project for which he got the recognition for the diploma and small prize. This recognition will be also for the best project this year, for the best project submitted, so just take the example.
Okay. Congratulations. Can you win it twice?
Yes.
Okay. So there's tough competition.
Okay, myself Shomin Bhattacharya from VCC Kolkata, India, and I just start my career as a gamma ray spectroscopist, experimental in nuclear physics. So I just want this course help me to interpret my experimental data to know more about the physics in nucleus. Thank you.
Good morning, everybody. My name is Sylvain Leblond. I'm a second year PhD student working in a laboratory in Caen, not Gamil, just on the other side of the road. I'm an experimentalist. I'm working on light nuclei, neutron-rich light nuclei, and I'm looking at unbound states in particular. Just to mention, as I'm not the only one, but as I'm living in Caen, if ever you have questions about, as mentioned, what you can visit or anything, or if you want to organize something, I would be glad to discuss with you and see what you're interested in and so on. I mean, I'm sure we can work together to have nice times. There's a lot of things to visit in Caen and just in Normandy, so feel free to ask.
Hi, I'm Mallory Smith. I'm from the University of Notre Dame. I'm a PhD student there. I work in experimental physics. I do gamma ray spectroscopy and micron measurements for understanding neutron-rich mass 100 nuclei.
Hello everybody, my name is Sarah Changuke. Well, I come from Royal Institute of Technology from Stockholm in Sweden. I'm a second year PhD theoretician. I'm working with parent correlation around Dripline.
Hi, I'm Lin Pei Yu. Obviously, the organizer makes my family name. Pei Yu is my family name.
Oh, okay. So what should we call you?
You can call me Lin Pei. Of course. I'm a second year PhD student in the University of Urs Pira in Finland. I'm my interest in in stochastic partial theory, so obviously I'm a theorist.
Okay.
I'm Adam Jones from Michigan State University. I am just finishing my first year of my PhD studies. And I've not done anything interesting yet.
Ever in life? Okay, I hope your empty life will be filled a little by this course.
Hello everyone, I'm Sofia Antisch. I work at GSI in Germany. I'm a theorist. I came from Croatia. I was working for my master, something more similar to nuclear structure. I was doing quantum phase transitions in nuclei. And well, actually now for my PhD, I'm doing the equation of state for high densities. So for now, neutron stars, and then after that, we'll finite nuclei. And well.
Hi everyone, my name is Nam. I'm Vietnam. Obviously, I'm Vietnamese. Actually, I'm a physicist engineer. I used to work 2 years in a private company, but it was so boring working on Excel or Word or PowerPoints. So, and I missed the equations so much, so I just quit and came back to university and asked my old professor if he still wants me. So he accepted. So this is my first year as PhD student, and I'm working on exotic nuclei. So I'm a theorist. This is a good one. Thank you.
Hello everyone, my name is Lasumi. I'm a PhD student at the University of Bologna. I studied SSP simulation principle of independence.
Okay.
Hi everyone. I have a strong Japanese accent. My name is Shin Watanabe, and I am a second year PhD student from Kyushu University, and I am a theorist. And I am researching on the shear evolution of neutron magnetic isotopes in and beyond the ionic inversion. Thank you.
Hello everyone, I'm Alexis Mersen. I'm a PhD student in Gany, and I'm working on the production embedding the computer. And so, like Sylvain, I'm new in Caen. And so, if you need help or have a question, or if you want to visit Caen or the region, I would be glad to help you.
Hi, I am Jesus Pereira. I am PhD student here at the MTC in Caen. I am studying bound states in carbon and salinity. I am experimentalist. My interest is focused in transfer reactions.
Hi, I'm Kostas. I'm a PhD student at Florida State University, and I work on the abination light nuclei morphology.
Hi, I'm Felipe Matos. I'm from Universidad de Concepción, Chile. I've been studying nuclear structure, and I'm interested right now in microscopy and the interacting boson model. I'm curious.
Hi, I'm Rosa Perez. I have been PhD student in Valencia, Spain, and I did my master in theoretical physics, but I changed to nuclear physics, and now I'm doing the PhD in gamma spectroscopy with Agatha detector.
Let's go from back to front.
Hi, I'm Robin Smith from Birmingham, England, and I'm doing an experimental PhD first year, studying the structure of very light nuclei, so beryllium-9 at the moment.
I'm Peter Humby. Just coming to the end of my first year of my PhD. I work at the University of Richmond in the US and a little bit at the University of Surrey in the UK. And I'm an experimentalist working on Samarium, which is around mass quantity.
Hi, I'm Ravita Ilieva, but I go by Riley normally. I just finished my master's at University of Surrey in the UK, but I spent some time at Yale doing some photon scattering experiments and looking at the dipole response of nuclei we were studying, but I looked at some theory there as well. I have finished with that now and I'm going to start doing a PhD at Surrey this October on slightly more explosive reactions and supernovas. But I'm still interested in the theory behind it. So.
Hi, I'm Stanimir Kislov, and I'm a PhD student in my second year in the University of Sofia in Bulgaria. I'm an experimentalist and I'm working on fast time measurements.
Hi, I'm Maciej Konieczka. It's better probably for you to pronounce my first name Maciek, so this ends on K, not J, which is not common in other languages. I'm coming from Warsaw, and I just finished my my master degree, and I'm working on isospin breaking corrections as one person mentioned, but in the DFT scheme.
My name's Justin Leeks from Michigan State. I just finished my first year of graduate school there. Since just a first year student, my research is still just beginning, but I'm interested in along the lines of high performance computing with maybe some no core shell model type calculations.
I'm Daniel Negra. I finished recently my PhD studies, and I'm working at the National Institute for Physics and Nuclear Engineering in Mogurele, Bucharest, Romania, on pairing and quartet correlations in atomic nuclei.
My name is Francisco Catalano. I study in Trento University. I come from Italy, of course. And I'm finishing my and, my field of study is igrons in general, and in the scheme of Monte Carlo methods.
Hi, my name is Udo Geier. I'm from Germany, from the Technical University of Darmstadt, and I'm working on gamma ray spectroscopy.
Hi, my name is...
Where are you looking to study? Where are you looking to study?
I'm a master's student, second year. Sorry.
Again, hi, my name is Tobias Beck, and I'm like Udo, a master student at TU Darmstadt in a group of Professor Pietrala, who will also be a lecturer here. And at the moment, I work on I look for the 2+ of the scissors mode in gadolinium 156. I guess it's one of Professor Pietrala's things he always wants to find. And I'm starting my master's thesis in October with dysprosium 162 and 64, concerning also scissors mode and pygmy dipole resonance.
Hi, I'm Vasil. I'm from Bulgaria. I study in Germany in University of Cologne under supervision of Julie. I just finished my first year in my master studies. So in Germany, it's like you don't really need to be extremely specialized at this point. But I'll be working with a nuclei erbium 160. This could be described maybe somehow geometrically with the geometrical model.
Hello, my name is Eduardo Coelho, but everybody calls me Tonio. So.
Calls you?
Tonio.
Tonio.
It's like Tony, but with an O at the end.
Okay.
I'm from Mexico, so it's weird. I don't use my name. But anyway, I'm a third-year PhD student, and my research is about a model-independent description of the form and transitional nuclei. So I'm a theorist.
Hello, everyone.
My name is Ruslan Magana, but you can call me just Ross or Bruce. I am Christian, and I come from Mexico City. I studied at UNAM, National University of Mexico. The topics which I just finished my master and I am starting the PhD. The topic that I am interested to research is about nuclear models, develop nuclear models, and trying to determine element matrix elements for nuclear reactions, like transfer reactions or beta decays or double beta decays.
Okay, wonderful. Did everybody get everybody else's names?
Yeah, sure.
Should we have a test? Okay, you'll get to know each other during the week, and I hope you'll all be friends for decades. Anything else preliminary we should do? Did I forget anything? Okay, so if you could turn off the lights so we could see the screen. I don't know how to do that.
Okay.
Is that visible? Doesn't seem too visible. So I'm going to disappear right now. Okay, good. Everybody can see that? Okay, so now let's see. I got to make sure I understand. So that's the. Can you all see this little greeny thing? Okay. Oh, where's the stick? Ah, good. I often prefer these primitive things. Okay, so this represents the school itself, and I forgot the word exploring, but okay. So I'm going to give the lectures today and tomorrow, and we have about 40 minutes before the coffee break, so I'll get started. Whoops, what did I do? Okay, so I'll get used to this. Okay, so today and tomorrow I'm going to give you an introduction to nuclear phenomenology and to some very simple models. The idea of this is that very often in textbooks you see a development of some theoretical apparatus and then some predictions, and then they come and show you some data which agrees or doesn't agree with those predictions. My feeling is that it's useful to know a little bit about the data beforehand, to see the landscape, so you know what it is that these theories are trying to predict, rather than have a theory predict something and show you a kind of random piece of data that fits it. So I'm going to give an introduction to what nuclei look like. I don't mean look like, but I mean what their spectra look like, and a little bit about their structure, and then introduce some simple models. Most of this will be tomorrow, and this will mostly be today, but we'll see how it goes, okay? And remember, I encourage questions. So this is an overview that applies not only to nuclear physics, but to many areas of modern science. There are two ways of looking at many body systems. One is a microscopic approach, where you look at the individual constituents and their interactions. And in nuclei, that means what is the force that binds nuclei, and why do nuclei do what they do? Okay? This is actually the subject matter of most of the talent courses so far. And it's a very important approach. A complementary approach is a macroscopic one. This should be femtoscopic, I guess. A macroscopic one where we look at the many-body system as a whole. We look at the nucleus as a whole with a shape, with vibrations, rotations, and excitations. And we try to assign quantum numbers and predictions for the system as a whole. And these nuclei exhibit remarkably simple patterns. We try to understand what those patterns are and what is their origin. Okay? So this is more a question of what nuclei do And this is more a question of why nuclei do, but those labels are a little bit fuzzy because both sides do both. Okay, so these are the two perspectives you can use to look at nuclei. I will focus mostly on this, but you will get plenty of this as well during the course. Okay? This is the plan for today and tomorrow. I want to talk about 3 key ingredients for understanding nuclei. These are very simple ingredients. I want to give a brief introduction to a couple of idealized models. Now, this brief introduction will be like 1 slide for each. And the only reason for that is to give you the names, a few pieces of jargon, so that when I discuss the data, the empirical behavior of nuclei, I can attach some labels to that behavior. But I won't go in any detail here about these models. Instead, I will come back to them after I've shown you the data and then go into those models in some detail. Okay? Okay, key concepts. These are the 3 key ingredients for understanding nuclei. Now, it's not everything, but this gives you a good start. One is that the nuclear force is short range and attractive. That is, nucleons, protons, and neutrons interact with each other when they're close to each other. That's a very hand-waving way of saying it, but it has the basic idea behind it. The Pauli principle is the second, which has 2 aspects. It controls the occupation of these nucleons in specific orbits, and it implies anti-symmetrization of the wave functions, and that has a big impact on residual interactions, and as you will see, is the reason basically why all even nuclei have 0+ ground states. And then 2-state mixing, or mixing in general. When we do a calculation of any aspect of nuclear structure, we start with some set of basis states. And we have a Hamiltonian. That Hamiltonian invariably mixes those basis states. And what comes out is a result of that mixing. It's the origin of collectivity, coherence in the wave functions. And the simplest one is 2-state mixing. And I'm going to go in some great detail on 2-state mixing because it's the basis for multi-state mixing. And in fact, very often if you do a multi-state mixing calculation, you can decompose it into approximately a sequence of 2-state calculations. And so I'll go through some formalism for this, and this afternoon there'll be some exercises on this in particular. Okay, so I said that the nuclear force is short range and attractive. How do we know that? Well, there's a lot of data that tells us that. But one piece of data is nuclear masses, which very simply give a clue to the range of the nucleon force. You will see this slide 3 times today and tomorrow with different aspects of what these masses tell us. But the total binding energy, or total mass of a nucleus, is the sum of all the interactions of all the nucleons in the nucleus. Mass differences are differences of masses between neighboring nuclei. Those are the same as separation energies. They can give evidence about shell structure, phase transitions. We'll come to that later, and this will also come to later. Now, if you talk about the total mass of a nucleus, each proton and neutron has a mass of approximately a GeV. That means a typical heavy nucleus has a mass of 150, 200 GeV. And excitation energies in even nuclei are on the order of an MeV. So it's pretty hard to learn much about that by looking at the total mass. One always looks at some function of the mass. And one is the binding energy, that is the sum of the energy required to remove each of the nucleons to infinity. And often the binding energy divided by the number of nucleons, the average binding energy per nucleus, per nucleon. So I want to look at that and show you a very simple plot, and we'll see that this immediately tells us that the nuclear force is short range. So this is about the simplest data you can imagine. It's a plot you've all seen. It's in almost every textbook. It shows the binding energy of a nucleus per nucleon divided by the number of nucleons. And it starts off, and the scale here is MeV, and this is 0, and that's 10 MeV. And so it starts off and it increases here, and then somewhere around in the region from oxygen to cadmium, it kind of flattens out. And basically, in first order, it's flat after that. There's a small drop, but we can approximate this as something going up and then flat. And I want to try to understand that and understand what it tells us. Okay? So I want to look at the simplest possible model you could imagine, which is clearly wrong. I like to look at wrong models because they often contain some essence of the real situation. So I'm going to assume that every nucleon interacts with n others, and we will look at different values for n. And all those interactions are equal. Now, you know that's not right, but we'll do it anyway. And we're going to look at the resulting binding as a function of n and mass. And we'll compare with this binding energy per A plot. Okay, so this is complicated looking, but it's actually very simple. A column is for the case of each nucleon interacting with a certain number of others. So this column corresponds to each nucleon interacting with 2 others. And I do that for a case of total nucleons 3, 4, 5, 6, and 8. Okay, I don't know what happened to 7, but okay. So if you have 3 nucleons and they interact with 2 others, this one will interact with this one with this and this one with this and this. Total of 3 interactions. And if I now divide by the number of nucleons, I get the number of interactions per nucleon is 1. If I go to 4 nucleons, each one interacts with 2 others. I have a total of 4 interactions. So the number of interactions per nucleon is 1. 5, I get 1, 1, 1, 1, 1. So if this were the case in nuclei, the binding energy per nucleon would just simply be 1. It would be this line here. So this is what you would get for the binding energy per nucleon if each nucleon interacted with only 2 others. Suppose each nucleon interacts with 3 others. Well, here there aren't 3 others to interact with, so that's the same. Here, this nucleon will interact with this one, and this one. And similarly, and you count the number of interactions, 1, 2, 3, 4, 5, 6. There's 6 interactions, 4 nucleons. So the total number of interactions per nucleon is 1.5. If I go to the next one, you can do it. You can work it out yourself. It's 1.4, then 1.5, then 1.5. If I plot those as a function of A, I get a line that comes up like this and then goes off constant, approximately constant at 1.5. If I go to 5 interactions per nucleon, I'm not going to do the counting and things like this, but here it's obviously 1 by definition because there are only 2 others. Here it's 1.5 because there are only 3 others. Here, if you count the number of interactions, you get 2 interactions per nucleon. The binding energy per nucleon is 2. Here it's 2.5. Here it's 2.5. And so you would get a curve that would go up like this and then be flat. And I wonder now whether I have a mistake here with 8 and 7, but it doesn't matter. You get the idea. If each nucleon can interact with all others, then every nucleon interacts with A minus 1 others, and they're A nucleons, so you have A times A minus 1 over 2 interactions. And if you divide by A, the number of interactions per nucleon, you get A minus 1 over 2, which is this line here. Okay, so you can already see from this very trivial way of looking at it that you have a curve, this curve here, where each nucleon interacts with all the others, doesn't look like this plot. It does look like the beginning of the plot. This curve where the binding energy per nucleon is constant doesn't look like this plot, but it does look like this part. Okay? And so what you see is that you can get a curve that resembles the data if you assume that each nucleon interacts with 8 or 10 others. Then the binding energy per nucleon would go up and then become flat. And so from this very simple counting scheme, which is hugely oversimplified, you can conclude that each nucleon interacts with 10 or so others. 10 could be 5, it could be 20, but that ballpark. Which means that the nuclear force is short range, and it's shorter in range than the size of heavy nuclei. Okay? So from just measuring the masses of nuclei, putting them on a scale basically, we can already tell that the nuclear force is short range. And it's obviously attractive or we wouldn't be around to ask the question. Okay, now two-state mixing. There's going to be some heavy formulas here. You will have these slides, so I won't go through every detail of the derivations. And anyway, you've probably all seen this. I want to present it in a slightly different way, which gives you some universal functions. Okay, so here's the problem we want to solve. I have two levels called E1 and E2 with Arabic subscripts, and they have an unperturbed energy spacing delta E unperturbed. They have unperturbed wave functions phi 1 and phi 2. Okay, now I assume that they interact with some interaction V. Okay, and what happens? You know that levels that interact repel each other, and so they will be further apart after mixing than before. And the amount they push each other apart I define as delta ES. S stands for shift. And the final energies are given by E1 with a Roman subscript and E2, and the final wave functions by psi 1 and psi 2. Okay, I want to define the quantity because this is really the key to everything. R, which is the unperturbed energy spacing divided by the interaction. And you will see that everything can be written in terms of R. So you all know the solution to this. I mean, this is really elementary, that the final two energies are given by 1/2 the sum of the initial energies plus or minus 1/2 the square root of the difference in those initial energies squared plus 4 times the matrix element squared. And I can take out, the E2 minus E1 is the unperturbed energy difference. So I can pull that out and I get, this is the same, I get plus or minus delta E unperturbed over 2, 1 minus 4V squared over delta E mu squared. So all I've done is just take this out of the square root out here and call it delta E mu. And now using R, I can write this as same thing. This is the same square root of 1 plus 4 over R squared. Okay? The perturbed energy separation, that is E2 minus E1, is then given by, so I'm just going to take this and take the difference E2 minus E1 using the plus sign in one case and the minus sign in another. I get that it's the unperturbed energy separation times the square root of 1 plus 4 over R squared. And now if I write the perturbed energy difference in units of the initial one, is this getting faint already? Okay. If I write the perturbed energy difference in units of the unperturbed, I get this, that the perturbed energy separation in units of the unperturbed is just the square root of 1 over 4R squared. Okay, you can go through the rest of this if you want. So this is a universal expression for the final energies in units of the initial energies, and it only depends on this one quantity R squared. Okay, and it doesn't matter whether the initial levels are separated by 3 electron volts or 22 GeV, or whether the interaction is a kilovolt or an MeV. You can always write it in terms of R. The only case where this doesn't work is if the two initial levels are degenerate, because then you have 1 over 0 there, and you have to use this equation. But other than that, it works universally. The mixed wave functions, psi 1 is going to be a linear combination of the two unperturbed wave functions with coefficients alpha and beta. Psi 2 will be the orthogonal mixture, minus beta phi 1 plus alpha phi 2. Have to have alpha squared plus beta squared equals 1. And this smaller amplitude beta is given also in terms of R by this expression. Okay? And now you can make universal plots. This shows beta, the amplitude of the smaller, as a function of R. And remember, R is the unperturbed spacing over the matrix element. So if the unperturbed spacing is large compared to the matrix element, you're over in this section. I'm having trouble with this. You're over.
Yeah, fading.
Okay, so I'll do that. You have the curve is here, corresponding to small beta, so the mixing amplitudes are very small. If the matrix element is comparable to the unperturbed spacing, so that R would be 1, you're down here, you have a very large mixing amplitude of 0.5. The largest you can have is 0.707. This shows the repulsion of the admixed states. So it's the repulsion, the shift in units of the unperturbed separation. And there are two curves on here just because to blow that up. The upper curve goes with the lower scale and the lower curve goes with the upper. And so you can just read off this plot for any case you want what the final energies or what the repulsion is, and since you know the initial levels, you can get the final levels. So this gives you a universal way of getting the final energies for any set of initial energies and matrix element. Okay, clear? Here's a table with some examples. These equations refer to equations in my textbook. Don't worry about that. So here are examples of cases for R, ranging from very almost degenerate levels to levels that are far apart. This is the shift in energy compared to the unperturbed energy. So if they're very close to each other compared to the matrix element, the shift is big. If they're very far apart, the shift is very small. If they're very close together compared to the matrix element, the mixing amplitude is large, and it goes down. Okay? Here I do a specific case where I take 100 kilovolts unperturbed energy separation, and then these R values correspond to these interaction matrix elements. If I have an unperturbed spacing of 100 kilovolts and R is 0.2, it means the matrix element was 500 kilovolts, 100 over 500. And in that case, the shift in energy will be 452 kilovolts. So these levels that are 100 kilovolts apart initially will each move by 452 kilovolts. That's a huge mixing. If I take R of 1, the wave function amplitude will be 0.53, and the levels will each move 62 kilovolts. If I take an R of 10, the wave function amplitude is 0.1, and each level will move 1 kilovolt. Okay, and you can fill in any other numbers you want here. This gives some nice examples. Okie dokie? All right. Here is a concrete example, which I don't think I'll go through, but it'll be in the slides. I take a case of two levels which are 200 kilovolts apart with a 50 kilovolt matrix element. So that's an R of 4, and that's in between 3 and 5, so you can already guess. Well, you can actually look at this and guess what beta is going to be. It's going to be somewhere between 0.19 and 0.29, and it works out to be 0.23. And the shift is going to be in between, where is it? The shift will be between 0.04 and 0.1, and it turns out to be 0.059. You can work through this, okay? It's just designed to give you a concrete example where you can actually work it out, okay?
Excuse me.
Yes?
I have a question. Previous slide. This, in the case of R equal 0.2 or 0.5, that is very large of shift is very large.
The shift is very large compared to the, yeah. This is a case where the matrix element mixing the states is larger than their separation.
Yes.
And they go,
Yes.
okay?
In this case, can we describe this case by perturbation theory?
Well, this is an exact answer because it's just two-state mixing.
Yes.
So this is exact.
Not perturbation.
No.
No, I think he has a problem because these formula are derived using perturbation theory.
Yes.
And in
Yeah.
this case, obviously, the interaction is maybe comparable to the Hamiltonian.
Yeah, but
compared to the interaction.
if you diagonalize the matrix, you get this.
Yeah, I think that this was the
Okay. I want to look at, two specific cases. One is degenerate levels. This will turn out to be very important. For degenerate levels, delta E unperturbed is 0, and so R is 0. You can't use the formulas with an R in the denominator, but you go back to the original ones, and you find out that the final energies are the unperturbed energy plus or minus V. That means the final levels are separated by 2 times the matrix element. So they are 2V. And that has a very interesting implication, which is sometimes very useful. Two levels that mix can never be closer than twice the matrix element. Okay? And in fact, this historically was very important in the study of odd mass nuclei, where the Coriolis interaction is important. There were levels that were found that were isolated two-state systems that mixed, and they were closer than twice the matrix element. And so that led people to understand you had to attenuate the Coriolis mixing. That has lots of other implications. In this case also, the wave functions are as mixed as they can possibly be because the initial separation is 0, and so beta is just 1 over the square root of 2.707. Okay? Another case which is very useful is weak mixing. That corresponds to R much greater than 1. And if you plug in the formulas, I'm not going to go through this, it's just algebra, you get that beta is 1 over R. Okay? So beta then is simply the matrix element divided by the unperturbed spacing. Okay? And the energy shift is the unperturbed energy shift divided by R squared. Okay? I'll do a couple of examples. So
this is perturbation.
This, yes. So suppose you take R of 10. Okay? These are approximate formulas. Suppose you take R of 10, then this formula would give beta of 0.1, and it would give a separation of 0.01. The exact results, yes, thanks for saying that. The exact results are beta equals 0.0985 instead of 0.1, and this quantity 0.0099 instead of 0.01. So for R of 10, these formulas are essentially perfect. Even for R as small as 3, this is where the initial separation is 3 times the matrix element. That corresponds to pretty big mixing. These approximations give you beta of 1 over 3 or 0.33, and the energy is 1 over R squared, 1 over 9, which is 0.11, and the exact values are 0.29 and 0.101. So even for quite large mixing of 0.33 amplitude, these formulas are pretty good. Okay, and so these are very, very useful guidelines to always keep in your mind when you're looking at nuclear levels and their mixing. Now, real nuclei have more than 2 levels, and they mix. What time is it? Oh, we've got plenty of time. Okay. And they often mix with each other. And so then you're typically solving a matrix like this, which you have to diagonalize. And the final wave function will be, just like before, it'll be a sum of amplitudes of all the initial wave functions with different amplitudes. The details will depend on the interactions and on the energies. I want to discuss one important case where all of these levels are degenerate. Now, that's not a realistic case, but it contains the essence of a lot of physics we'll discuss. And so this is what I would call an extreme toy model. If you apply it in a realistic case, you would get answers, like for samarium, you would get answers like 10 to the 14th, whereas the real answer is 200, so it's approximate. But, but it contains the essence of the physics. So suppose I take n degenerate levels, and suppose each one mixes with all the others equally. So if I have 5 levels, this one would mix with this by interaction V, this with this by V, this with this by V, and so on. They would all mix by matrix element V. What happens? What happens is this. 4 of them go up by an amount V, and of course you have to conserve the total energy. So 1 of them comes down by n minus 1 V. Okay? This, and the wave function for this level, is all equal amplitudes of all of these basis states just with a normalization factor. This is the essence of collectivity in nuclei. You have a set of states which mix. One state comes down, its wave function is all in phase, and it has the collectivity of the whole system in it. Okay? And you will see this again and again and again. And thinking about this will instantly, as you'll see, help you understand the entire evolution of structure across the nuclear chart. So that's what I just said, absolutely fundamental result, foundation of collectivity. coherence, collectivity, and the energy lowering all grow with n, goes down as n minus 1. So the more states you have interacting, the lower the collective state will be. And as I said, this largely explains a lot of the general features of the evolution of structure. I want to apply this to a calculation of a transition rate. So let's assume I have n degenerate levels. Okay. And we know what the wave function will be. It will be this, where a, this normalization factor, is 1 over the square root of n. And I want to calculate, let's assume there's a ground state which is not mixed, and these are 2 plus states. I want to calculate the transition rate from the final 2 plus state to this ground state. I'm not sure all of you know this notation. Does everybody know what a BE2 is? Anybody not know what a BE2 is? It's no embarrassment. Okay. So a BE2 is the notation we use for the square of a transition matrix element. It's related to the transition rate, but there's some other factors that go into the transition rate or the lifetime. But it's defined as 1 over 2 times the initial spin plus 1 times the square of this reduced matrix element from 2 plus to 0 plus. Okay? I'm going to calculate without the square first. So the matrix element itself from this 2 plus to this is going to be the matrix element to the 0 plus with this mixed wave function there. And so I can write that, since this mixed wave function has this simple form, it's just simply A times the sum over all the individual matrix elements. Is that clear? Okay. And now I'm going to make the approximation that all these individual ones are equal. That is, the matrix element from each of these initial unperturbed states to the 0 plus is the same. And I'm going to call that, I think I call it, yeah, okay. I call it W. I don't know why I called it W. Okay, so now I take this, each one of these individual ones is W, and so I get that the matrix element is N, because there are N components here, A, W, NAW, and when I put in the value for A, 1 over the square root of N, I get that this is the square root of N times W. The BE2 is the square of this. I guess I've dropped a factor of 5, but it doesn't matter. So the BE2 is proportional to N W squared. So that says that the transition rate from this final mixed state is N times the transition rate from any one of these. Okay, or I shouldn't say transition rate, I should say the BE2. So that's an enhancement of N. If N is 5, that's an enhancement of 5. If N is 10 to the 12th, that's an enhancement of 10 to the 12th. And you will see that this is a gross approximation. Gross doesn't begin to describe how gross it is. But the idea that the collectivity of these transitions increases with the number of states that you have to start with persists. Okie dokie? Okay. It's a fundamental property of collective states. Okay, so that's a kind of quick introduction to two-state mixing. And now I want to start to look at some of the data. I want to look at nuclear level schemes, how they change with proton and neutron number, what the challenges for theory are, and especially what are the key observables for testing theories. And I'm going to discuss later on, mostly tomorrow, some geometrical models in some detail, and today I will discuss the independent particle model as well. My discussion of the independent particle model will be very simple, and I don't want to say hand-waving because I use the word hand-waving to mean what you say if you don't know the answer, but it will be, let's say, extremely simplified. Pete, later in the week, will give a much more formal presentation of the independent particle model, and also we'll both talk about residual interactions. First, to try to describe the data without any understanding of the physics of what's going on is very difficult. So I want to bring in a couple of slides on basic models without deriving them or anything, just sort of like a deus ex machina pulling it out of the sky, just to give you some labels, okay? Okay, first of all, what observables will we look at? When you study nuclei, you have to measure something. There are a lot of things you can measure. These are not all of them by any means, but they're the ones that I will talk about most. Masses are one thing, and we will find that we can learn a lot about nuclei from their masses. We already learned that the nuclear force is short range and attractive. We will find out later on we can go much, much further. All nuclei have a ground state, which is good. They have excited states, and these are it's not a real nucleus, it's just a random example. Almost always, I'm talking about even nuclei. I will discuss, in the third week, I'll discuss odd mass nuclei. Almost always, I would say 99% of the time, the first excited state is 2+, and probably about 97% of the time, the second excited state is 4+, and then you have other states. Okay? So we will look at these states, their spin imparities and their energies. One important measure of structure, which does not tell you everything, but it's a good first guide, is this quantity R42, which is the ratio of the 4+ energy over the 2+ energy. So in this case, it's 2.5. Okay? I stress that whenever I look at an even nucleus and ask myself what's going on, that's the first quantity I look at. But it's very important to understand it doesn't tell you everything. Okay. Very important also are BE2 values, basically transition rates from these various states. Okay. Typical notation is the thicker the arrow, the bigger the BE2 value. That's a common practice. Okay, so these are the observables, most of the observables we'll look at. Okay, now the idealized models. They're basically two classes. There's the independent particle model, which is just a model of nucleons running around the nucleus in orbits. And that's the foundation of sort of nucleon-based picture of the nucleus, the shell model, if you want. And I will go into some detail on that. And then there are collective models, where this model becomes impractical. You resort to collective models. Remember the very first slide I talked about a microscopic and macroscopic approach, one looking at nucleons and their interactions. This is the simplest version of that. I mean, utterly simple. And then I talked about a macroscopic picture where you look at what the many-body system as a whole is doing with its own quantum numbers. That's collective models. And I'm going to talk about two collective models right now, very, very briefly. A harmonic vibrator, and what you should picture in your mind there is a spherical nucleus that can vibrate. Okay, and that's all I'm going to say about it basically for now. The other simple model is a deformed rotor. What I mean by that is a nucleus that's shaped like, and I'm sorry to have to get patriotic about this, like an American football. All of you know what an American football looks like? Anybody not? Okay, so looks roughly like an American football. And since it's non-spherical, it can rotate. It can also vibrate, and so you get both of those kinds of excitations superimposed on top of each other. These two are collective models. They involve things going on in the nucleus as a whole, and this is a nucleon-based picture. Okay, so some spherical nuclei are quite rigid, but many of them are soft. Soft means that they can oscillate a little bit. Later we'll talk about this in terms of a potential, where you have a potential, the nucleus can oscillate back and forth, but right now I want to be very qualitative. They can be soft to vibrational motions. The lowest such excitation is a quadrupole excitation, so that's an excitation where you take a sphere and then it looks a little bit like the American football this way, and then looks like it this way, and goes back and forth. That has 2 units of angular momentum, and so the first excited state will be a 2+ state. Now, there's no reason why you can't have 2 of these excitations superposed on each other. And so if you superpose 2 of these quadrupole spin 2 excitations, which can be called phonons, you get a 4+ state. And since you're just superposing 2 of the same thing, the energy of the 4+ state is twice the energy of the 2+ state. And that's a 2-phonon state. There are other 2-phonon states which we'll talk about, but for now, just look at this. And clearly R42 is 2.0. So just bear this in mind. I will use this kind of language to talk about some of the nuclei we'll see. Okay. The other is nuclei are three-dimensional. That means they can rotate. And rotational energies in nuclei. So I'm picturing now, just to make it very clear in case some of you are confused, here I have a roughly an American football-shaped nucleus. It's not exactly. By rotation, I do not mean this. I mean this. Okay, a quantum mechanical object can't rotate about a symmetry axis. So it's a rotation like this or like this. Now I got to orient this back the right way. Okay. Those energies follow the energies for the quantum mechanical symmetric top, which means that the energies of these rotational states go as h bar squared over 2 times the moment of inertia times j plus 1. Comment here that I should have made before. I use the letter small j to mean the angular momentum of a nucleon, and large j to mean the angular momentum of the nucleus. Okay, sometimes in the literature you will see a large I. Typically, but not always, people who use large I are or have been interested in high spin states, and those who use J tend to have been interested in low spin states. That's not a rule, but it's common. And now I want to use this simple formula and just get one result very quickly. Suppose I put angular momentum 0 in here. Can anyone tell me what this is equal to? There's a hint here. Everybody see that? Okay, suppose I put angular momentum 2. Well, it's going to be proportional. I don't care about that. 2 times 3. Can anyone do that without a calculator? No? Somebody want to tell me? 6, good. And now a little more complicated, 4 times 5. What?
20.
Oh, I thought you said 7. Okay. 20. Okay. So the 2 plus should be at an energy. Sorry? What?
It's of the order of 90%.
Yeah, okay. 7 and 20. We'll see later that those differences tell us something. Okay. So the 2 plus state will be at an energy proportional to 6 and the 4 plus 20. Now it gets a little tougher. The 4 to 2 energy ratio is 20 over 6. Can anybody guess what that could be? Okay, 3.33. All right, so that's a very simple result for a rotational excitation. And okay, we do it that way. And here's one example. There's this formula again. This is nobelium 254, and here you see this rotational band. And what I do here, and you'll see this more later, I normalize this 2 plus, this is the formula. I normalize this 2 plus to this energy. In other words, I use this excitation energy to establish what h bar squared over 2I was. And then I calculated these levels. And you'll see they agree very, very well with the data. You will also see that they disagree slightly. This 8 plus is a little higher. We'll understand that very soon. Okie dokie? All right. So that's, well, this isn't doing anything, so. Okay, so now I want to look at the empirical evolution of structure. And this is a good place to stop, so let's have a coffee break. Be back here at 11, and we'll look at what real nuclei are doing. Was that agonizing for your theoretical soul?
Can I maybe ask you something?
Of course.
Okay, can I check something on the slide? On the slide?
Which slide?
I was looking. Actually, I saw this in your book.
How far back?
It's the beginning. It's just the oh my God. Here. I think this one is wrong. You see.